Very good. So let's get started with the third day of the course. In the previous 2 days, we have discussed reproducing kernel Hilbert spaces, the main properties of these spaces. We have seen a few examples. On the first day at the beginning, I motivated why it would be interesting in machine learning to use reproducing kernel Hilbert spaces. So today we are going to continue with the machine learning point of view and starting to use these spaces of functions. Okay, so let's go back 2 days to the beginning of the course, and then let's see what we said at the beginning. So we were thinking about supervised learning. Right. The way I introduced the problem was like there are two sets, X, we can call it the set of instances, and then Y, the set of labels or classes. We are going to use something very simple, so just two different classes. Right, so just two different classes, and then the idea was that we want to. The idea is that we want to find a classification rule that is a function from X to Y, and we also said that finding that classification rule is the same as finding a function from X to the reals, because we are going to use functions that are just given as the sign of some function to the reals, and that's why we started to discuss a lot about the functions from X to the reals, and we discussed sets of functions that are reducing kernel Hilbert spaces, and that was useful, etc. Right? So, okay, so we have set of instances, set of classes. We want to find a classification rule. What else I said? Okay, so we want to find this, and then we have at our disposal to do this. We have some examples. So we have n examples. We have 10 examples that we call the training examples. Right. And this is called supervised learning because in the examples that we have, we know both the X and the true Y. We have a teacher that is telling us what is the right label, what is the right class. Okay, and then I also mentioned that the usual approach is called empirical risk minimization, and basically the idea here is that we find the rule or we find the function that minimizes the empirical loss, and the loss depends on the examples that we have and on the function that we use. Okay. So the first day, the loss function that I was mentioning was the 0-1 loss. Let's write it again. So the 0-1 loss is 0 if f is right, since we are just interested in the sign. F of x is correct if the sign of y and the sign of f of x are the same. So basically the product is positive, and the loss is 1 if the sign is different. So this is the example that we did before. And in this course, we are not going to discuss much about the losses, but just to have a more realistic example in mind about the loss. This is not something that is often used in practice, because as you can imagine, trying to do this optimization over this loss, that is complicated, because this is not even continuous or anything. So this is complicated in terms of optimization. A loss that is more common in practice is, for instance, logistic loss. In the logistic loss, basically what you do is you do something like this. See if I do it right. The specific reason why this is useful, I don't think we are going to talk in the course. If you have curiosity, we can talk about it. But basically, the idea here is that, well, this is more tractable than that, and it does something similar. So, for instance, if the sign of these two quantities is the same, this is a positive number, so that when we are taking the negative of it, this becomes negative. So this is a small quantity, and then the log is small. And when the signs are different, this is positive, so that the exponential is a big number. Okay, so the loss of this is big if the sign is different, and the loss is small if the sign is the same. Okay, so these are physical minimization in one line. And then we also said that there is a problem, a main problem, which is the problem of overfitting. We just mentioned it very quickly, but now we are going to talk more about it, overfitting. So the problem of overfitting, in the first day I just mentioned that this type of approaches can break down, because, for instance, I could, if I just try to do this, I could choose a function that is like this, is a function from x to r, and this function, what it does is for every training example, it takes it to the label that we have, and then for the x's that are not one of the x's are training, it does whatever, for instance, exit one. So this function is great in terms of minimizing this loss, but is bad, right? So, okay, and then, okay, so this basically what we said on Monday at the beginning. Now let's keep going with these ideas. I put some empty things in the middle because we are going to keep doing this, and to make the course a little bit less math dense and maybe more interactive, let's try to talk about these things together and see what's happened, right? So in here, so this is the formulation I mentioned on Monday, but Monday I missed multiple things because I just wanted to motivate the need of using this type of function. There are multiple things in this problem formulation that are missing. Well, maybe not multiple, but a few of them. I guess several of you know what the things are missing, but let's talk maybe first about it. Well, so first thing is on Monday I said that this is a bad idea, and nobody said and that he disagreed, and I guess is rather intuitive that this is not a good classification rule. But what makes this thing bad? So one of the things that we are missing here in this problem formulation is that, I mean, I am saying what we want to do, what we have to do it, but for instance, I'm not saying how we are going to measure if we are doing it well or we are doing it bad. So the other day I said this is bad, but what I mean with bad or good, or what makes a classification rule to be good or bad. And this is something that we have to be very clear about it, right? Because otherwise, otherwise it would be very simple, right? I mean, you just give me any function and that's it, right? So, and this thing we were saying is bad, but why is this bad? What makes this bad? Yeah.
Because it generalizes very poorly.
In general, yeah. Okay, so let's talk about it. So when you say generalizes, yeah, that's what people in machine learning would use. So generalizes would mean that, so that's great in the examples that we have, but those examples we already know what's the true label, so they don't really matter. When you say generalizes, I guess you mean that for x's that are not there, is going to work back, right? Okay, so that's an idea. Well, but I mean, but that's not necessarily true, right? I mean, it could happen that this works very well also in the other axis, or not.
You mean if we have only ones in the new y's?
For instance, right? So, I mean, could that happen? I don't know. I mean, at first it could, right? I mean, so this, I mean, so your point is that, yeah, I mean, this in general, this will work very badly, but maybe if we are in that case in which all the x's that are not in here all correspond to one, maybe this works well. Right. So in that case, that can be a good idea. Okay. So let's think a little bit more about that case. So in that case, in the case in which the x's that are not here are all one, in that case, this would work well, but this will work well by chance, right? So basically, we are trying to use the training examples to learn something. In this case, this thing would work well, not because we have learned anything from the examples, just because we got lucky or whatever, and this thing, right? So in the cases in which this works well, are not really cases that we care about, because in the cases in which this would work well are cases in which we are not learning anything. Okay, so let's talk a little bit more about that. So, I mean, we are trying to learn something from examples. We are trying to learn something from examples. What make us think that that's even possible? So, I mean, we just have some examples. Why, from some examples, we think that we can learn something that works for other cases? Yeah. Okay. Let me think again. So, in order to find the classification rule, we just have examples, right? Some examples. 1,000, 10,100, 1 million, maybe 50, whatever, right? From those very specific examples, we are trying to learn something that is useful in general, right? For other examples, why that should work? What makes us think that there's something like that should work? That from what happens in some examples, we get something that works for other cases. Is that something that, yeah?
Because we believe that the data follows some underlying function. So we believe that we might be able to extrapolate something similar to the function that the data follows with the sample.
That's one way to put it. Yeah, so you
there is some kind of relationship between X and Y, and we can learn.
Okay, so let's put these ideas. I think both of you are saying something similar, and also I like the fact that people are participating. So basically, you are saying that if we assume that there is a underlying relationship between the x's and the y's, right? Like maybe there is some, how should I call it? So if we assume that the y's are generated from the x's using some kind of function, right? If we assume something like this, and maybe this g is nice in some sense, maybe smooth or something, then maybe doing something with some examples, we might get a function that is somehow similar to g, right? So that's one way to think about it. But that way is not the best one. So that way is not the best one for a couple of reasons. So first of all, so in here, so right, so we will assume that y is related to x through some function, and then our goal would be to estimate the dg, right? So get some g that is somehow similar to the g in some way, right? So that's okay, but that's not really what we care, right? So this is so if you like, this would be so this g is how the y's are generated from the x's, right? If we think in the example of the email filtering I was mentioning the other day, so maybe this g is describing how what makes an email to be a spam or not, right? So that's like what is the process that makes an email to be a spam, right? So if we try to estimate that g, we would be trying to know what makes an email to be a spam or not, or what is the mechanism that makes an email to be a spam or not. I mean, if we can do that, this is good. I mean, if we know how the emails are what happens in the minds of the people generating spam filters, I mean the spam emails if we know how this generative mechanism works, then we can use our estimate for this generative mechanism to make predictions, right? But we don't really care about what makes an email to be a spam or not. We just want to be able to predict if some X is a spam or not, right? So we are trying to do something easier than this. Okay, let's think, because this is kind of interesting. And this, so the first day I mentioned the first chapters in Babnick's book, so he talks about these things a lot, and I think that's also what makes the book interesting. Let's think another example that I like a lot. So is the example of learning the colors, right? So when children, when they learn the colors, the way they learn the colors is that the parents tell the small kids, okay, this object is green, this object is blue, this object is red, right? So the way that we all learn to distinguish the colors of the objects is because our parents at some point show us multiple examples of some objects, and they told us, this is red, this object, this is blue, right? And then after some time, they just show us, they just point to the object, and we have to tell what's the colors, right? And we could all learn to distinguish the colors, right? But the way we learned to distinguish the colors was not by trying to learn what makes an object to be blue and what makes an object to be green, right? So we didn't have any idea of that, and maybe we still don't know anything about what makes an object to be of one color or another, but we all know what is the color of each object just by seeing examples, right? So this is maybe okay, but this is maybe more than what we really want. And in addition to be more than what we really want, this is problematic because we will need to assume that the people generating emails or whatever are using some kind of a smooth function to generate spam emails or something like that. So this might work, but this is not the best thing we can do. Okay, so what make us think that just from examples we can learn something that works for other cases? And for this, before we continue with discussion, there is an example that is also very interesting. In some island in the Pacific, maybe you have heard about this example. In some islands in the Pacific, very small islands, people that live there, they have like religious, I don't know, celebration or something. They have some religious act they do, and basically in these ceremonies, what they do is like they go in the island to a flat ground without trees or anything, and then they put fires into parallel lines. I don't know, maybe some of you have heard about this, so it's pretty interesting. Okay, so they do this, and then they put fires into lines, and then they hope that putting these lines of fire is going to give good fortune. Okay. So why they do this? Well, so in the Second World War, the Americans or the Japanese, or maybe both, went to those islands, right? And then they went to the islands and they did exactly this. They put 2 lines of fire in that specific place. And then after some time, some airplanes came in here and they gave food and other goods to the people there. Right? So, and they are still doing this thing. So basically, they saw some examples. So they saw, okay, if you put fire like this, you get food, right? So then they thought that putting fire like this creates good fortune, right? So why we expect that we are not going to be in one of these situations that using examples we are actually going to learn something, not just to replicate what we see and
Because then you are learning, let's say, by comparing. You have some samples that belong to an underlying distribution. You assume that the new samples that you have to classify belong to the same distribution. So it's kind of, okay, this sample looks similar to this one, so I will classify it in the same way.
Yeah. Okay. So you said several things important in what you said. So let's be more specific about that. So in here, so of course, learning from examples in general is impossible. For instance, in the case of the email, I can very easily give you as many examples of emails as you like, and I'm sure you are not going to learn to classify emails in spam or not. For instance, I can send you many emails I send with my friends or whatever, or maybe none of them are spam, and you can have as many examples as you like, but you are not going to learn to classify emails. Yeah, of course. Yeah.
I think that what you said relates to some hypothesis of stationarity of the data, which is that it behaves similarly in the train and the test. And so, for example, to take the email example, if we take a classifier with of the 1990s, it would be like, I don't know, a Nigerian prince, some diagram ads and stuff like that. And then if we had a spam of today, it could be, I don't know, NFTs or Bitcoins or whatever bullshit it is.
Sure.
And a classifier of the 90s might be unable to discriminate. Well, there would be a lot of exclamative points, but well, except of that, it would
Right.
So
So that's I guess basically what you are saying is that the examples that we use at training have to be somehow similar to the examples that we are going to try to predict later, right? Right. So we are going to be specific in a minute, but yeah, that's so it's like, for instance, in the example of the learning the colors, right? So if the parents if the parent, so I mean, the examples have to be similar to the examples you are going to see later, and also being somehow general enough. Right? So for instance, if the parents in the example of the colors, when they are trying to, when they give examples of the green color, they always point the grass, for instance, right? So if the only example they show to the children is the grass, when they mean green, it's very likely that maybe the kids think that green means grass. And that's also related with the example of the island in the Pacific, right? So maybe if they have some other examples with other ways to where they get the food or something, they might learn something different, right? So the training examples have to be somehow similar to the examples at the test, at the prediction, let's say. And they also have to be somehow generic in some sense. Right? And yeah, I think these are all the good ideas, and I think Jose already mentioned what we are missing here. So, how to fix, how to make this right. So basically, the examples that we have cannot be whatever. So they have to be random. Have to be random samples, and the easiest case is if they are independent and they all follow the same distribution, and let's call that distribution here. So in the previous 2 days, we were using linear algebra analysis and so on. We never use anything probabilistic or statistical or anything. But I want to explain this slowly to show that the probability or statistic is very basic for these things, right? So without it, we can't even explain what we are trying to solve. Okay, so basically, if these samples are random and they are independently obtained from one distribution B star, then is it possible? I mean, possible means, is this we are going to be in that scenario in which something like this is a good classification rule. So this would be a good classification rule if for these examples the labels are like this, and for the rest of examples are always one, right? But if the examples are obtained randomly, of course, if somebody is choosing the examples, yeah, you can have this problem, right? But if these examples are obtained randomly, how likely is that we are going to be so lucky that the examples that we have are exactly the ones that are not one? Right? So if these examples are random, the true situation cannot be like this, or the probability that the true situation is like this is very, very small, right? So if the good situation is the situation in which most of the x's are one, in the training examples, if they are randomly obtained from here, most of the y's are going to be one. Not like this, right? Okay, so this fixes this kind of problem, right? And for that we need this, and yeah, and then the other thing that we need is basically we want to find a classification rule that and the way we are going to measure if that classification rule is good or not is basically we can compute the loss of our classification rule in examples, and in the most simple case, we are going to have a situation in which the examples in which we are going to do prediction follow the same probability as the training example. That's what we were mentioning before, right? So the examples at training have to be somehow similar to the examples in which we are going to do prediction. The way in which they have to be similar is because they come from the same distribution. this can be make it weaker. The distribution does not need to be exactly the same, but in the standard formulation. Okay. So, okay, yeah, question, yeah.
I still don't understand why that framework is wrong, because I understand that we are not interested in the cost, in how Y's are generated, but function G could represent the external characteristics of X that make us be able to recognize, for example, an email is spam or not, or a color is green or not. And we have to assume some kind of regularity in how X and Y are related, right?
Okay, fine. Okay. Yeah, so basically you are saying that this G does not need to be explaining what makes an X to be Y and so on, right? It can be just a way to identify what, right? Right. So this, okay. Okay. Yeah. This I can buy it, and this could be like, for instance, the best possible classification. Maybe not something generating the X's from the Y's, but it might be the best classification rule. Yeah. So I mean that can be done. Small problems with that. I mean, I don't know if it's small, but some problems that this other formulation don't have. If you want to approximate this function with this other function, you have to assume something like about continuous or whatever, differentiable or alpha. And here I'm not assuming anything about the relationship between the X's and the Y. Other thing. I am what?
You are assuming a conditional distribution.
I am assuming that they are random and that they are following the same distribution, but this distribution can be whatever. I don't assume this is simple or tractable. So this is just any distribution, but so yeah. So this P star can be whatever. I'm not assuming anything. Yeah, other small thing about this. In general, it happens that for the same X, we might have different Y's, because maybe if X is some keywords in the email with the same keyword, sometimes the email is spam and sometimes it's not, right? So we cannot really model exactly the relationship between X and Y with a function. Even less if we try to assume that it's somehow smooth or simple or something, right? So okay. So yeah, okay, good. So okay, this is good that we have this conversation. So I mean, this way of doing things is okay, but this is slightly better. We need to assume less things. So basically, the only thing that we assume is that these are random, that the examples are random, and that the ones are training are independent, and in the standard case, so our life is easier if the distribution is exactly the same as training a test. The distribution don't need to be exactly the same, but in what we are going to do in this course, we are going to assume that they are exactly the same. Yeah. Okay, very good. What else? Okay, so now if we are in a situation like this, right? So what give us hope that an approach like this can work? What give us hope that an approach that is minimizing this expression can work, right? So we are trying to find let's do it with. So we are trying to find a function that has a small expected loss when the x's and the y's are following some distribution, right? And the way we are trying to do it is by minimizing this empirical average. So now it's clear what gives us hope that this can find an f that is going to give a small value here, right? So what gives us hope is that, well, usually doing averages of IID samples, give us something similar to the true expectation. And for that, it's also important that these things are independent and so on. So if these are independent and from the same distribution, we have a mathematical machinery that can tell us if this is similar to this. If we don't have this part, we are overrun, right? So if those are just examples, right? How we prove that this is going to give us something good. Mathematically would be not possible to prove much, right? So, okay, so all this is trying to explain that the formulation is like this for good reasons, and also the necessity of going to the statistics and probabilistic real. Okay, very good. So yeah, so from now to Friday, in addition to linear algebra and analysis, we will also have the statistics and probabilities because we really need it. Okay, so now let's see how. So basically, from this discussion, I guess it's kind of clear that the way to avoid these kind of problems is to make sure that the sample averages are similar to the true expectation. For instance, in this very simple example here, if we do the sample average of this loss with this function, okay, let's write it. So if we use this function, the sample average, if we use this function, the sample average of this loss, of the 0, 1 loss, it will be exactly 0. Right? For this function, if we use this loss, we will be always in this case, because this is perfect in the training samples. So the sample average will be 0. However, the true expectation will be not 0. Will be depends on the distribution, but in general this will be pretty different. I mean, I don't know how to say. So the true error will be in general much bigger than 0, right? And the cases, so the case in which the error of this would be near 0 would be these cases in which almost all the x's are 1, but that case is very unlikely, because for that case to happen, we will be so lucky that the training samples are none of this part at all. Okay, so in this case, these two things are very different. So in order to avoid overfitting, basically what we need to ensure is that we work with functions that ensure that the sample averages are always similar to the true expectation. And that's where the reproducing kernel Hilbert space come to help us to avoid overfitting. Yes.
Well, maybe it's not so related. Is there a way with this kind of formulation that you can learn unseen classes? Like, let's say, okay, you have like a problem in which you have like 3 classes, and you just get examples from the 2 first classes. Can you use this formulation to learn something like, okay, if this sample is like, let's say, far away from the rest, I will guess that it belongs to the 3rd unseen class.
Not easily, right? So basically, what makes us life easy to prove things, at least theoretically, is that the samples at training follow the same distribution as samples at test. You are talking about a situation in which in training, we don't have any sample from the third class, but at test, some samples are for the third class, right? So in those cases, it's like the distributions are not the same because at training, we don't have any example.
Or maybe that you have very less samples at training, so that this like third distribution, the probability of having one sample from the third distribution, it's quite small, but then at testing you have much more samples, so maybe you have few of them. So is there a way like not to overfit to that class, let's say?
So if the distribution is the same, if the distribution, if I mean, if you are saying that from the third class, I have very few examples, right? And maybe I only have 1% of the examples are from the third class.
Yeah.
If at test also from the third class, only 1% of the examples are from the third class, then yes, this all we are going to say is still valid. The problem would be if at training 1% of the examples are from the third class and at prediction, and maybe 40% of the examples are from third class. Because in that case, the distribution at training and test will be different. You can deal with this, right? You know, possible to deal with it is, but not with the tools I'm going to explain in this course. Okay. So in this course, I'm going to assume all the time that the distribution at test is the same as the distribution at training.
So if you have that both are the same, but you have this 1%, and let's say you
Yeah.
have 50 training samples and 1,000 test sample, how would you not overfit to that class, let's say?
Just as yeah. So I mean, we are going to prove that these two things are similar with high probability, and that the similarity depends on the number of samples that you have. So of course, if you have very few samples, every now and then you don't have any example of the class 3, and then in those cases you are not going to learn anything, right? But basically, these two things are going to become more and more similar as we have more and more samples and with higher probability.
Just one thing, that the problem you mentioned is often encountered in general machine learning, not talking about RKHSs. And a way to deal with that is to adjust the loss function,
Right.
so that you put some more weight to the
Right.
under represented class.
Right.
So for example, if you want to predict new problems with a nuclear reactor, you don't want to predict correctly the 99% when you have you have no failure. You want to predict the problematic times.
Right.
And so there are lots of recipes in, for example, people who do neural networks and stuff like that to deal with that problem.
Right. So yeah, indeed, Jose is working in somehow similar type of problem, right. So I think the question of Jose is if the Dutch framework formation can be used for the problem that he is working. So as I said before, it's not mandatory that the distribution is exactly the same at prediction at training. The distributions have to be somehow similar, or at least you have to have an idea of how different they are, in order to compensate and so on. We are not going to discuss this in this course, but I mean, it can be done. We are going to do just the simple case in which both distributions are the same. Okay, great. So, okay, this was a good discussion. We still have time to do some math after this. So let's do something more precise about why this the empirical average has to be similar to the true expectation, and what makes reproducing Kernel Hilbert spaces useful to avoid those type of problems. Okay, so basically we want the true expectation. Let's write it. Let's write it with some so that later I can write other things. Let's put it here. So basically we want that the expectation of some function, the difference between the true expectation and the sample average over some n IID samples, we want this thing to be small, right? So that's our goal. And we want it to be small, not only for some specific f, we want it to be small for any f that we are going to consider, right? Because we are going to find the f by doing some optimization problem. So we would really like that this is small for the solution of that optimization. One way to ensure that is that this is small for any function, right? So we might want to have that in the worst possible case, as we go through some set of functions. So one way to avoid this overfitting is to make sure that in the worst possible case, as we go over some set of functions, this is bounded by something that hopefully decreases with the number of training samples. Okay, so this is the kind of thing that we are going to try to bound. Okay. And basically, we are going to be able to bound these things as long as the set of functions is simple enough. Of course, if the set of functions is a finite set and we only have 10 different options for the functions and so on, this can be done easily. We are going to do it in cases when G is complicated, very large representative space. Yeah, you are looking with things. Yeah, so what's the... So maybe it's just... So the notation is clear?
Just f is the function that generates the y's from the.
Yes, okay. Yeah, no, okay. Yeah, let me be more specific. Okay, so before we were talking about the loss functions, right? So before we were talking about the loss functions of some f of x and y, right? So in here, what is random is the x and the y, and we have a loss besides the f and so on. Okay, so what would really want to do is, instead of this f, have this loss, right? And we would like the true expected loss to be similar to the average of the loss. In the theorem I'm going to prove, I'm going to do a somehow easier case in which I will only consider a function over x. Okay? So the thing I'm going to prove is initial step towards proving the case with the losses and so on. So the steps I'm not going to prove are basically not very long, but I don't want to have a very long discussion. Basically, use some properties of the loss, like the ditches and so on. Okay. Yeah. So I'm going to do the step that I feel is more interesting. The rest is you can find in any book of machine learning. Yeah. Okay. So yeah, instead of, let's be more specific, we would like to bound this thing. We would like to bound this thing, right? I'm going to do this step just about the function f. How you go from a bound from here to a bound from there is just a couple of more technical steps. And for those, you need some properties of the loss and so on.
Just
Yeah.
to make sure I understood. Well, I totally understood that you are going to prove that in order to give us the intuition to step towards the more complicated result. But in itself, it doesn't have any practical utility, because, for example, if I take I don't know if I don't know, maybe I'm wrong, but if I have it's the same f, right? Okay. Okay. It's the same.
Yeah, but we are going to consider the worst case, the worst possible error. So if you like, this is the case in which so if we define g of c to be the loss of f of x y and z are pairs x y. So okay, I'm just okay. So of course, I mean, this result is interesting, and the proof is also interesting. That's why we are going to. Okay, so let's do this because it's slightly more simple than the case that we really care, and also we are going to use this type of results tomorrow. Okay, so let's try to prove these things. I mean, to bound the things. So the way we are going to bound it is using something that people call Rademacher complexity. So let me see what what is this, and then maybe we go for a coffee before the proof. Okay, so this is this. Plus times and now I'm going to explain what these things mean. Square root. I think I got the constants right. If not, it doesn't really matter much. Okay, so let's call this a theorem, and this is Rademacher uniform concentration. So in statistics and machine learning, basically, when you try to bound the difference between the true expectation and the sample average, that's called a concentration bound. This we are going to call it uniform because basically we want to bound it for any f. So we are going to have a bound that is valid for any f. More things. This quantity here is called the Rademacher complexity of the set of function. And let's give the intuition why this describes how complicated are the functions. Well, before that, I have to explain what is sigma. So the sigmas, so we have n sigmas. The sigmas are going to be IID values from uniform distribution that takes value -1 or 1. So it takes -1 with probability 1/2 and 1 with probability 1/2. So this quantity here is measuring the complexity of this set of functions because this thing is going to be big basically when for each pattern or signs or plus minus signs, I can find some function in my set that follows the same pattern or signs. So this quantity here is big when if the sigma is positive, I can make the f very positive, and when the sigma is negative, I can make the f very negative, right? So basically, if you want to make a picture, you have some samples, right? And then for some samples, the sigmas are going to be positive. For other samples, the sigmas are going to be negative, etc. Right in here, I'm putting the values of the sigmas, right? So this quantity here would be big. So if no matter what random signs I put here, I can always find a function in my set that is very positive in here and then goes to be very negative and then is positive and then is negative again, right? So that's okay. And I can always find a function that follows the patterns of the signal, right? These are going to be generated randomly. So that's why this quantity here describes the complexity of my set of functions. Basically, this is very large when the functions can follow any change on the signs. Okay. As in here, the expectation is taken with respect to the x's and also with respect to the sigmas. Okay. The intuition of why this quantity measures how complicated is the set of functions. Kind of clear. So basically, this will be very complicated if my set of functions can change sign as we like. Okay. Questions, comments? Yeah.
The function that like takes the supremum in the left side is not needed to be the same as in the right side, right?
No. And we are not, I mean, we are not going to try to even find that function or anything like that. That would be too complicated. These things in general are very complicated objects. We are just bounded. We are just going to bound it. Okay, okay. So this is the meaning of this Rademacher complexity term. For the last term, I am going to explain what n is. So basically, G is a set of functions from X to R, and basically what happens is that the functions are going to be bounded by that value n. So all the functions in my set are going to be bounded by n, and that's going to happen for all the x's. And then the result says that with probability, at least 1 minus delta, we have that one. Okay, so this is the result. And maybe after the coffee, I'm going to prove. Sorry. Okay. Let's get started with the proof and finish after the coffee. So basically in the proof, again, I'm not going to do all the steps because I'm just going to do the interesting steps. So basically what I'm going to prove, is that the expectation of the sub, okay. So maybe before that, let me make one more comment about this one, right? So the thing in the left is a random number. It's a random number because the x's are random. Maybe I should put it in the statement. So x1, x2, xn are IID from E star, if you like. And then here I'm doing the expectation with respect to the same distribution example as I promised you. Okay, so this quantity in the left is a random number. It's random because this thing here is going to be random. This is not random, this is just a constant, but this thing is random. So what's going to be the highest value of this is going to depend on the specific x's that we have. So this thing is going to be random. This expression in here is not random, this is a constant. I'm doing the expectation over the x's. Right? So this is saying that this random variable is most of the time, with probability at least 1 minus delta, bounded by this constant.
Just one question. So if it is constant, it means that the sigma I are fixed as well?
I'm doing the expectation.
Okay, I did not see that. Okay, okay.
The sigmas are IID. In here, I'm doing the expectation over both the x's and the sigmas. So what is in the right side is a constant. I'm saying that this random variable is bounded by this constant with high probability, so that if I want to be more sure, I will need to increase this last term, etc. Okay, so basically what I wanted to say is that I'm not going to do the whole proof. I'm just going to prove that the expectation of this random number in the left. So let's put another expectation more. So now the expectation here is going to be with respect to the x's. The expectation of the supremum. And yeah, this is not really needed. So I'm going to prove that in expectation, so I'm going to prove the boundary in expectation. the x's and also respect to the sigmas. Basically, well, if I don't write with respect to what I'm doing, the expectations I'm doing it with respect to everything that is random. Yeah, sigma I f f. Okay, so after the coffee, I'm going to prove the bound in expectation. To have the bound in with high probability, in addition to what I'm going to do after the coffee, you have to use something called McDermott inequality. So, as I said, I mean, these results you can find in almost any book in machine learning. So if you are curious, you can check there. After the coffee, I'm going to do that step of the proof because I think it's the most interesting to do. Okay, good. So maybe now we can make a pause of some minutes. Okay, so let's keep going. Let's prove this. I want to do the proof because it uses interesting ideas and also steps that appear multiple times in similar proofs. So I think it's good for you if you see this with some detail. Okay, so let's go ahead and prove it. The techniques to use this to do this kind of proof is kind of interesting how people call it. So they call it ghost. Ghost. We are going to use ghost samples and symmetrization. Okay. So the idea is kind of interesting. Yep.
So just to clarify, the outside expectation is over X.
Yes.
So the inside one is also over X.
The
So
inside
expected value of X, that's gonna be already a number or?
So this is the expectation of this part over that variable. So this is the true expectation of f, and this I'm going to take the expectation over the remaining thing that is good. Yeah. Okay, so yeah, ghost samples. So the idea here is that basically the term you comment before. So this is the true expectation of the variable f of x. So we can write this as the expectation of some samples x1 tilde xn tilde. So these are going to be IID samples from the true underlying distribution of x, and these samples don't really exist. Right? So these are not the training samples or anything. These are just examples that we use for the proof. Okay. So if you like, you can say, let's imagine x1, xn are some IID samples from P star. So these are going to be independent and also going to be independent. Well, they are independent, so they are going to be also independent of the other x's. Okay, so these are what people call ghost samples because it's not that they really exist. This is just for the purpose of the proof. So so if we have n IID samples from the same distribution, this term here so this term here we can write as the expectation over these new samples of the sample average of those samples. So this, what I'm doing here is straightforward. It might look a little bit strange, maybe because it's not clear why we are doing such a change, right? But I hope it's clear that this quantity in the left here is the same as this. We just change the expectation by the expectation, over some n IID samples of the sample average. So the expectation of the sample average is always the true expectation, right? So then these two things are the same. Okay. So those are the ghost examples. So the reason why we introduced these new examples is because later we are going to basically bound these differences here. Okay. Okay, so this is like the first step, and then we are going to use well. So in here, so before we do Jensen inequality, here we are doing the expectation of this part, right? With respect to the x tildes, this part here is a constant, so we could as well just put everything, right? So the expectation of a constant is that constant. So put in the parentheses there, of course, it's not changing anything, right? So now we are going to use Jensen inequality. I guess Jensen inequality is very familiar to most of you, but since it's important, let's see what the Jensen inequality does. So Jensen inequality. So basically, Jensen inequality. Question? Yeah.
No, I was joking. I knew it one day in the past, but
Yeah, no problem. So we are going to do it. So I mean, we are not going to prove it, but we are going to see what it is. And also with the picture is very simple. So Jensen inequality basically says that if I have a function that is convex, I'm going to call it a G. So if I have a function that is convex, right? If I have a function that is convex, now there is a relationship between doing the expectation of the values of G and doing G of the expected values of X. Right. And to remember where to put the sign, I always need to make the figure because so okay, the function is convex. If I am doing expectations of the values of the function, right? If these are values of the function and I do average of these values, I'm going to be above the curve. If I do the value, right? So X is here. If I do the value of the function G in some specific X, I'm going to be in the curve. So this is smaller than this. This is just a mnemotechnic thing. To prove it, you need to do some work, but okay. So this is Jensen inequality. And of course, this is if G is convex and if G is concave, it's the other way around, right? Because a function is concave when changing the sign becomes convex. And this inequality is used multiple times, basically. As long as we have expectations, it's something that comes later. Okay, so let's do this. Basically, we are going to do this in here. So the sup is a convex function, right? So if I'm doing the sup over, let's put it like this, over some f of something of a convex combination of something that depends on f, and I do the convex combination with something else that depends also on f. This should be clear that so basically the sum of the sum is always smaller or equal than the doing the sum, doing this supremum independently. Right, so this sup in the left is smaller than this other sup, basically because in here I am forced to use the same f for this term and for this term, while in this other case I am allowed to use one f for this term and a different f for the other. So I can always make these sups bigger or at least equal than in this other. Right. So the sup of the sum is smaller or equal than the sum of the subs, and then in here, well, I didn't say it right, but to prove that something is convex, you consider convex combinations, right? So the alphas are a positive number, 1 minus alpha is also a positive number. I can now move them outside of the sup. Not going to write it there, right? So the sup is a convex function, right? This is the definition of being convex. So the sup is a convex function. And then we use Jensen inequality when G is the sup. So the sup of the expectation is smaller or equal than the expectation of the sup. So we can move the expectation outside and do the expectation over both the real lexes, if you like, and the cost ones, if you like. And that's right. And now we have what we wanted. We have made everything about the differences between pairs of F. Okay, so I just moved the expectation outside of the sup using Jensen. Okay, so now we are in better shape. So now, in here I'm doing the expectations of the sub, and in here we have differences between F at some points and F at some other points. Both the X tilde and the X's are independent of each other. So the distribution of this difference is the same as the distribution of that difference if I multiply by +1, I am not doing anything. If I multiply by -1, in terms of distribution is exactly the same, right? It would be like changing the order, but in here there is no difference between X tilde and X. Both are IID samples. I am doing the expectation over all of them. So calling something X or calling it X tilde is just a matter of taste. So is it clear for everyone? If I put in here either a +1 or a -1, I'm not changing the expectation, right? Because the role of the X's and the X's tilde is the same. I can change the notation. So putting here a +1 or a -1 doesn't change anything, so that I can put a different +1 or a -1 in every term of this sum. Nothing will change in terms of the expectation. And since I can do it for every sign that I like, and I can also do it if the sigmas are random, and nothing will change. And then I can also do the expectations over the sigmas. So these are going to be in the theorem the sigmas that are either +1 or -1 with some probability. Okay, I hope this was clear. Put in there the sigmas don't change anything. So okay, so now let's yep, sure.
Why did you add sigmas?
Well, the reason why I added it is because I want to prove.
Oh, yeah, I know.
Why can I do it, right? Okay, yes. So so the X tilde and X are both the same object, right? All of them are IID samples from P star, right? And I am doing the expectation with respect to all of them. So in here, putting a -1 just means that I will be doing the difference between this minus this one, right? So and the order of this difference don't matter because the X tilde is the same as X. So if you like, I could change the name of the X's and nothing will change.
Okay, but you're not doing an expectation over sigma.
Well, so that is true for every +1 and -1 that I choose to use. Is going to be true also if the sigmas are random, and is going to be true also if I do the expectation, because nothing will change. Okay, right? So yeah, this proof is interesting like this. Okay, so now we have this. Next step. So this is what is inside of the soup is going to be sigma if xi tilde, and then in here we will have +1/n minus sigma I xi. Well, I just did it, and now, well, we said it before, right? So the sum of the sum is smaller or equal than the sum of the subs. So in here we have the sum of this sum. So that is going to be, should I write it? This should be possible to see. I think yes, this should be basically the last step. So I'm doing the expectation over everything. And now the sum of the sum is going to be this sum of the sub. So we will have expectation with respect to the x's and the sigmas of the sub of 1/n, 1n sigma I tilde. Let's put first the tilde, and then plus the expectation of the sum is the sum of the expectation, and then the sub 1/n minus sigma I f as xi. Right? I just use the fact that the sum of the sum is smaller than the sum of the subs, and use the fact that the expectation of the sum is the sum of the expectations. So we are basically done, right? So this is one of these guys. This is one of these guys. Now this other thing, if the sigmas here are either +1 or -1 with probability 1/2 each, right? So the theorem is so the Rademacher complexity is remove it. So the probability of being +1 and -1 is the same. So in here it doesn't make any difference if I put minus or I put plus, right? I'm doing the expectation over them. So then these two things are the same, right? So because calling the x is x tilde or calling the x is the same, both are the same thing. So this is the same thing as this. So that's why we got the two. Okay. Okay, that's good. This is the proof. The proof is not really complicated. It's just that somebody had the ideas of doing it like this, and that's what makes it work. Okay, very good. Can I ask one? Of course.
So then, like in the last step, you would have a equality, right? Like from going like for €2 there to the 2 times the expectation, it would be.
Yeah. Right. Yeah. Yes. Okay, great. So now let's use this result to prove what we were really after, which is the fact that if we are using a reproducing kernel Hilbert space, we can ensure that the sample average are always close to the true expectations. So this was just a preparation result. It's interesting by itself because maybe you want to use something that is not a reproducing kernel Hilbert space. So Rademacher complexity is not only for reproducing kernel Hilbert spaces, of course. Okay, so now let's do theorem. But this is let's call it uniform concentration in the producing kernel. Okay, so we are going to do bound like before, but in the specific case in which the functions are in a reproducing kernel Hilbert space. So H is going to be a reproducing kernel Hilbert space given by kernel K. And in here, and so yesterday I mentioned that the norm in the reproducing kernel Hilbert space help us to control the smoothness of the function. I talk about that when we talk about the Gaussian kernel, right? So functions with a small norm are smoother than functions with a bigger norm. So yesterday was just like a interpretation of the Gaussian kernel, but basically this result is going to work when we consider functions in the Hilbert space and the functions have a bounded norm. So the norm is going to be smaller than some number b. So we are going to do it for balls in the reproducing kernel Hilbert space. Okay, and then we will have the same thing as before. We will be bounding the difference between expectation and sample averages. And maybe it's more common to represent it with absolute values. So we will be bounded these differences. And now the result is that this is smaller or equal than 2 times b times m. M I mentioned yesterday, so basically m is a bound for the diagonal elements of the kernel. So m, so the diagonal, so basically we have a kernel and the values of the kernel is bounded by m squared. And yesterday I also mentioned in the example that also how big is this is also related to how complicated are the functions in the kernel space. We found we told, for instance, that this constant describes the better if I told you, right? So yesterday we were saying that if I have a function in the reproducing kernel Hilbert space, the point-wise values of the functions are bounded by that constant m and also by the Hilbert norm, right? So, for instance, we were saying that the values at the specific axis can be controlled if we control the norm, but they will also depend on how big is this thing. Okay. Okay, so now everything that we said that the past 2 days are going to appear in one way or another. So this is bounded by this, and then we have 1 plus square root of 1/2 log of 1 minus delta divided by the square root of n. Something else I'm missing. Then, so basically the thing is that we have, so with probability at least 1 minus delta, we have this in.
So in very hands down perspectives, it means, for example, that when you are doing machine learning with many methods, you always tell the students, so take a training set, take a test set, and then you train on training and you test on the test, or you do cross validation or whatever.
Right.
And it means that when you are doing stuff with RKHA field, don't care about that, you just have your training and you're able to, or not.
Well, I mean, you always care about that. So basically, so you always, I mean, when you do, I mean, this is just a theoretical results that tells you that if you increase the number of training samples, the difference between the in sample error and the out of sample error is going to decrease.
Okay.
That doesn't mean that in practice you will compute the training error and then estimate the out of sample error by using this inequality,
Okay.
because this in practice is not going to be tight.
Okay. So it's like MCMC. You know that it will be okay when n goes to infinity, but what does infinity mean, right?
Yeah. So I mean, this is, I mean, this is basically for the theoretical purposes, if you like. It's always nice. I mean, this kind of bounds are not only for the Rosen-Kernel spaces. Basically, I guess every reasonable method will have a bound like this, because otherwise it's like we will end up in the problems we talked at the beginning of the talk, right? So if what happens at training is not really related to what happens at prediction, it's like right? We cannot really learn anything. So one way or another, at least for the classification rule that our method finds, these two things should be somehow related. So in practice, this is not a quantity that you will use to estimate the true out of sample error, basically because these bounds might be, these constants might be too big, or maybe even you don't know what B is.
Yes. Okay. So
You might.
cannot,
So tomorrow, I guess, yeah, it will be tomorrow. So tomorrow I will be talking how you use these ideas in practice, but basically in practice, you use some regularization or something like this, but you don't know exactly what is the norm of the thing. Okay. So, yeah.
That constant n, which is the norm, does we have that constant for any arc HS or
No, I guess no. I mean, so you are asking if there are kernels that for which there is, you cannot uniformly bound for every x. I guess yeah, there are. I mean, there are so many different kernels people use, but yeah, this is. I mean, this is not necessary to define a representative kernel space, right? So yesterday we saw the four ways to characterize a representative kernel space. This was not a condition that you need to, right? So if you remember, okay, so to be more specific, right? So one condition that you need is that the evaluation functional, so evaluation functional at f is bounded by some constant that depends on x, and then some and then the Hilbert number, right? So that's what we saw. That if you have this, that's a representation space. If you have this, or if you have that, basically means that this constant, you can find a constant value for all the x's. So that's stronger. So yeah, you don't. So yeah. So you can have representative spaces in which you don't have this, and then yeah, this bound will be useless.
but how is that possible? You will always have m of x.
Yeah, but x can depend on the, and you got, I mean, this constant can depend on x. So, right. So this constant could be,
Okay.
I don't know, maybe the norm of x or whatever, right? So, and then if your x's can be very large, you cannot find a constant that bounded for all the x's together. Right. So yeah, that's a good point. So I mean, this is a result. Yeah, I said here in RKHS, at least if you can bound this. Yes. Good. Yeah, this is a good point. Okay, so now, yeah, let's do the proof. So of course, for the proof, we are basically going to use the previous result. Well, the first little thing in here, I put the absolute value because I think it's maybe more common, but so I put the absolute value in the previous results. I was not doing it with absolute value. I was just bounding it without the absolute value, right? Thing is that in this specific case, when the family of functions is like this, it doesn't matter if you put the absolute value or not, because if f is here, minus f is also going to be here. So the difference between, so the, right, so what, let me see. So the absolute value is either in this order or in this other order, right? Depending if it happens in the positive or negative, but this is in this order considering the function minus f, right? And if we are in a Hilbert space, if we are in a Hilbert space, f and minus f have the same norm, so okay. So both f and minus f are here, so okay, it's clear to everyone that it doesn't matter to put the absolute value or not. Okay, so this is this. So now let's use the previous result. So the previous result basically says that that quantity there, right, is smaller or equal than the Rademacher complexity that was 2 times the expectation of the stoop over f. Write it again. Okay, let's be more compact. Just the norm is smaller than b, and then 1 over n sigma I f x I, and then we had the term 2n square root of 1/2 log of 1 delta. Right. Okay, so this is just using the previous result. The n, if you remember, the n was bound for the values of the functions in the family. Now we have this bound here, and f and the norm of f is like this, so we can take as n the m times b. So the n in the previous result is going to be m times b. So that's something. So now basically the only thing that remains to be done is to bound the Rademacher complex. So let's do that. Okay, so I'm writing too much, but it doesn't matter. So we are so I'm going to just bound the Rademacher complexity. I'm doing the expectation over the x's and over the sigmas of the sub of 1 over n sum sigma I f x I. And the f have Hilbert norm smaller than b. So let's do this. Where should I? Okay, let's write it here so that I don't. So basically, f evaluated at each point, we know using the reproducing property that is the inner product of f with the section corresponding to the point xi. Right. Using the reproducing property that we have seen many times in the last 2 days. So now we can use the linearity of the the inner products. Well, first of all, the 1/n, I'm going to move it out of everything. So expectation, and then the sub of the inner product between f and the sum. The 1/n I already move it out, and sigma I k xi. Right? And we are doing this sub over. Right? I'm just using the linearity of the inner product to go from here to here. Okay. So now we are going to get rid of the sub. So before we got rid of the sub using just Jensen and so on, now we are going to get rid of the sub, taking into account that we are doing the inner product. We are doing the sub over things that are in a ball. So something that we can do is I can multiply and divide by b here and here. So if I'm doing the sub of the inner product of something that has norm smaller than 1 with respect to this other thing, right? So I'm doing over all the functions that have norm smaller than 1, this quantity, this sub is going to be the norm of this thing, right? Oops. This is just okay. This is just like, I don't know, the fact that in a product space the dual norm is itself its property, but I guess this is familiar to you, right? So basically we use that to get rid of the sub, and now we have the b here because okay, I need to have the norm to be 1. Okay, so we are almost there, and then to finish, we are just going to use the Jensen inequality. So the norm of this sum is not very easy to work with, but with the square is very easy. So we can just do the square root of the square of that. Okay, and now we are doing the expectation of the square root of this. A square root is a concave function, right? Since the square root is a convex function, we use a Jensen inequality, and then we get b divided by n, and then we get the square root of the expectation. Oh, I'm missing something. Sorry, I'm missing the sigma, right? And the expectation of the, okay, let's write it in more step. The expectation of the norm of sigma k xi of the sigma square, right? So this is just using Jensen for the square root. Okay, and we are almost there. So this is b divided by n square root. Should I do the expectation? Yes, do the expectation. Expectation. And now this norm square of a linear combination of the sections, we know how to compute. It's just the sum of sigma I times sigma j for all the pairs ij of k evaluated at xi, xj. Right? This is also the kind of thing that we were using yesterday and the day before, right? So the norm, if we are using combinations of, okay. All right, so we are basically done. So in here, we are doing, I put it at the beginning, but then I didn't keep putting. So we are doing the expectation over the x's and also over the sigmas. The expectation of the sum is the sum of the expectation, so we can put the expectation inside. And I'm going to do first the expectation with respect to the sigmas. So if I do the expectation with respect to the sigmas, okay, I'm going to do it just saying it. So the sigmas are independent, right? So the expectation of the sigma I times sigma j is the same as the expectation of sigma I times the expectation of sigma j. This is because the sigmas are independent, right? Now, the expectation of each one of it, since they are uniform, either -1 or +1 with probability 1/2, the expectation of each one of these is 0. Is 0, right? Because they are either +1 or -1 with the same probability. So the terms corresponding to different I and j vanish. And we only get the cases in which the I is the same of the j, and if the I is the same of the j, we always get 1. Because the sigmas are either -1 or +1. Okay, so I said this thing works. I hope it was clear. So basically, at the end, we get the sum, but just over I, and the sigmas are gone, and we get the expectation over the x's of I think. Yeah, I think this is maybe related with them. David's question before. Okay, so we get this. The sigma disappears because the cross terms are 0. When I is the same as j, is always 1. So we got this. Now we have the expectation of this kernel over x, right? So I'm going to bound this in a very simple way because I am assuming that the kernel at x in here the x's are the same, right? Because the cross terms have disappeared. So I'm going to bound this quantity very simple using this, right? If you don't have this, you might be able to have a bound for this by other means. But I guess that would require to assume something about the distribution of the x. But since we are in a case in which these quantities are always smaller than m squared, I'm going to bound this I'm going to bound this with m squared, and now we are doing the sum over n terms of m squared. So this is n times m squared. So that at the end we get n times b divided by square root of it. And that's what we need, right? So this is the right. The other term was already well. Here is the empty one. Okay, so the proofs are not really complicated. They are Jensen and a few steps, and we are using the properties that we mentioned multiple times the previous days. Okay, so basically the conclusion is that we can control this. We can control these differences if we use reproduction kernel Hilbert spaces, and also if we control the norm of the functions. Okay, so I think this is basically why we can avoid overfitting working with this type of function. And just to finish, I'm going to advance a little bit what we are going to do tomorrow, and then this. Okay, so basically, after what we discussed today, we realized that if we work on reproducing kernel Hilbert spaces, we can avoid overfitting. If we control the norm of the function that we use to define classification rule. So basically, instead of using just the empirical risk minimization approach I wrote before, we are going to use something that people call structural or regularized ERM. So basically, the plan is going to be, we are going to find the classification rule or the regression rule by minimizing over functions that are in a kernel representing Hilbert space and also that have somehow reduced the norm. Let's do it with this one. Right, so the plan is going to be at training, we are going to minimize the average losses. And we are going to constrain ourselves to functions that have a reduced norm, right? To avoid the possible overfitting. So today we saw that if we do this, this is a reasonable thing to do. At least we know that the behavior over the training examples is going to be similar to the behavior outside the training examples, right? So that's the progress we were discussing before, right? So at least if we constrain ourselves to use this type of functions, we know that we are going to learn something. And just to finish, instead of solving the optimization problem like this, the standard way to do it is to move the constraint over the norm to the objective as a penalization for high norm. Okay, so that's regularization. So why these two things are equivalent, you can see it using just Lagrange duality kind of thing. Very simple. Of course, it's not easy to know what is the lambda corresponding to the B here, right? So the smaller the B here, the bigger the regularization. So this parameter is usually known as a parameter, as a regularization parameter. So if we make this small, that one will be big and the other way around, but exactly the relation is not clear. So that's also what I meant before with the fact that you might not know this B. In practice, you always know this lambda because it's something that you can use. Well, I guess you can estimate. Yeah, I mean, maybe you can estimate, but that's it. At the end, the bound is not going to be that tight in practice. Okay, so this is the type of problem that we will do at training. And tomorrow, the first thing I'm going to do is to show how this problem can be done tractably, right? Because in here, this optimization is over functions in this Hilbert space. So how to do optimization over functions is not easy at all, right? So in here, the variable is a function. So the number of actual variables that you will need to use in principle would be infinity. So that's the problem, right? So tomorrow we will see how this problem is equivalent to a finite dimensional problem that's called the representer theorem. So today we talk about how to avoid overfitting. Tomorrow we will talk about how to solve these problems in practice. Okay, so if there are no questions, then maybe we can,
Like, can you choose or pick a family of functions, like maybe restrict a bit like more the Hilbert space, like to be sure that this B is not huge?
Well, in here we are choosing the B. I mean, choosing the B is the same as choosing the regularization parameter, right? So choosing a big regularization parameter is going to be like choosing a very small b. So choosing a big regularization parameter is going to avoid overfitting. So you will be more sure that there is not going to be overfitting. As you know, if the lambda is too big, yeah, there is no overfitting, but maybe the function that you find is not really useful. So if we choose a lambda that is very large, this b is going to be very small. So we will be only using very simple functions in our reproducing kernel space. And yes, the performance at training is going to be similar to the performance at prediction, but a very bad performance in both cases.
You were saying that the B was linked with the smoothness of the kernel you were using, right?
Right.
Okay, so it means that, well, if you have a pointy kernel like the exponential kernel, you will have some more overfitting than.
No. So, so B is something that you choose independently of the kernel that you are using.
Okay.
So, I'm saying that inside the same reproducing kernel space given by some kernel, you can tune how complicated or how simple is the function by tuning the norm.
Okay.
So yeah, this we saw it yesterday for the example of the Gaussian kernel. So basically, choosing a smaller norm in that case means to have less high frequency components in the function. Okay. So, yeah, the videos are going to be in YouTube. Yeah, so when they're in YouTube, you can check because otherwise it will be a little bit long. Any other question, comment? Okay, so then let's stop here. I continue tomorrow.